The event horizon is the most mysterious boundary in the universe. It is not a physical wall you can touch, but a mathematical point of no return. It is defined as the region where the escape velocity required to leave the gravitational pull exceeds the speed of light. At this distance, even light, the fastest entity in existence, cannot escape. Here we see how trajectory relates to speed, illustrating why reaching escape velocity is mandatory for leaving a gravitational field. Space and time are not fixed platforms, they are a flexible fabric. Gravity is the curvature of this fabric. Normal mass like the sun creates shallow curvature. A black hole creates an infinite funnel-like distortion. At the event horizon, space-time geometry warps violently. Light cones, which represent all possible future paths, tip toward the center. Inside the horizon, the roles of space and time effectively swap. Forward in time is now literally directed toward the center. You are pulled toward the singularity because it is your future. Gravity is so extreme that moving away from the center is as impossible as moving backward in time. At the core of a black hole lies the singularity, a point of infinite density. Here, space-time is warped to its ultimate limit. In this extreme region, our current mathematical models for gravity and quantum mechanics fail to coexist. They break down completely. This incompatibility signals that we are missing a fundamental piece of the puzzle, a theory of quantum gravity. The singularity remains the ultimate frontier of modern physics, challenging everything we think we know about reality. The information paradox is a central mystery in physics. Quantum mechanics states that information is always conserved, while general relativity suggests that anything falling into a black hole is lost forever at the singularity. Two main theories attempt to explain this. One suggests total information loss as the black hole evaporates. The other proposes that a firewall or quantum encoding captures information, preventing its destruction. Current research largely suggests that information is not lost. Instead, as matter enters, its quantum state is effectively encoded onto the surface of the event horizon, preserved even as the whole evaporates. The holographic principle suggests that our universe's laws may be encoded on a lower dimensional surface. Applied to black holes, it implies that the 3D volume inside is a projection of 2D data stored on the event horizon. Information falling into the black hole does not vanish. Instead, it is preserved as complex patterns on the horizon's surface, effectively acting like a 2D memory bank for the 3D interior. In this framework, the interior volume is essentially a hologram, generated by the entanglement and distribution of data on the event horizon itself. For years, a major debate persisted in physics, the firewall hypothesis. It suggested that, due to quantum effects, the event horizon of a black hole might act as a high-energy barrier that would incinerate anything falling through it. Recent advancements in holographic duality have largely dismissed this idea. Instead of a violent barrier, current models propose a smooth event horizon governed by quantum entanglement. Information is no longer seen as destroyed, but rather as being preserved through quantum states that connect the black hole's interior to the exterior radiation. The ER equals EPR conjecture is a radical proposal in modern physics. It suggests that Einstein-Rosen bridges, or wormholes, and quantum entanglement are physically equivalent. This theory posits that what we perceive as quantum entanglement between particles is fundamentally a microscopic geometric connection in spacetime. If entanglement creates these bridges, then space itself may be emergent. Entanglement acts as the quantum gum that stitches the fabric of reality together. Ultimately, this conjecture shifts our view of the universe from a collection of points in space to a vast network of interconnected quantum information. In his final years, Stephen Hawking proposed a revolutionary solution to the information paradox known as the soft hair theory. He suggested that the horizon is not smooth but covered in soft hair, low-energy quantum fluctuations. These fluctuations act as a storage system, preserving the quantum information of everything that crosses the horizon, effectively keeping it encoded on the surface. Black holes are not strictly black. They emit thermal radiation due to quantum effects occurring near the event horizon, a process known as Hawking radiation. Near the event horizon, quantum fluctuations create virtual particle pairs. When one particle falls into the black hole and the other escapes, the escaping particle becomes real radiation. Because the escaped particle carries energy away, the black hole loses mass over time. This process is known as evaporation, continuing until the black hole disappears entirely. The Page curve is a landmark discovery in quantum gravity. It tracks the entanglement entropy of a black hole as it evaporates over time. By plotting entanglement entropy, we see it initially rises as the black hole emits radiation. But crucially, after a certain point, the curve falls. This proves that information is not destroyed, it escapes encoded within the radiation. This validates that the black hole functions as an information archive, effectively resolving the long-standing information paradox by demonstrating that the interior is linked to the external universe. Deep inside a black hole, quantum information undergoes a process called scrambling. The black hole acts like a super-efficient processor, quickly spreading distinct pieces of information across all available quantum degrees of freedom. While the information appears lost or chaotic to an outside observer, the process is fundamentally unitary, meaning the original data is theoretically preserved and recoverable. The Event Horizon Telescope has successfully captured the image of the supermassive black hole at the center of our galaxy, Sagittarius A star. This wasn't possible with a single telescope. Instead, an international network of radio observatories synchronized as a single Earth-sized instrument. What we see is not just a void, but a complex environment of swirling gas and plasma spiraling into the event horizon. By measuring the size of the black hole's shadow, we found it aligns perfectly with the predictions of Einstein's general relativity. This milestone proves that even in the most extreme gravity, our understanding of space-time remains robust. When two black holes collide, they produce gravitational waves. The process occurs in 3 stages: in-spiral, merger, and the final ring-down phase. During the ring-down, the merged black hole settles into a stable state. Standard theory predicts a clean, fading signal. However, reanalysis of the GeV-20914 data suggests potential echoes in the signal. These secondary pulses could be the result of quantum corrections at the event horizon. If confirmed, these echoes would provide the first observational evidence of quantum effects in extreme gravity, effectively acting as a quantum signature of the horizon. The Laser Interferometer Space Antenna, or LISA, is a massive space-based mission designed to detect gravitational waves. LISA acts like a giant ear in space, measuring tiny ripples in the fabric of space-time caused by distant black hole mergers. When two black holes merge, they settle into a stable state. This process produces a specific ring-down signature, like a bell chiming. By analyzing these echoes, LISA probes the event horizon with unprecedented precision, allowing us to test Einstein's predictions about gravity in the universe's most extreme environment. We cannot travel to a black hole, but we can recreate their physics in a laboratory. Scientists build analog black holes using ultra-cold atoms or fluid dynamics. By creating a boundary where fluid moves faster than the speed of sound or light, we create a sonic event horizon. Nothing, not even sound waves, can escape the supersonic region. In this diagram, we compare astrophysical black holes on the left with sonic analogs on the right. Both share identical mathematical descriptions for how they trap waves and emit radiation. These experiments allow us to detect the elusive Hawking radiation. By studying how these systems scramble information, we are getting closer to understanding the quantum nature of gravity itself. In the vicinity of a stellar mass black hole, gravity behaves in ways that defy our intuition. The key phenomenon here is known as a gravity gradient. As you approach the singularity, the gravitational pull on your feet becomes significantly stronger than on your head. This difference, or tidal force, stretches you into a long, thin stream of atoms. This extreme tidal force is a consequence of the black hole's intense space-time curvature. It is the physical limit of structural integrity under gravity. To an outside observer, a clock falling toward a black hole appears to slow down. As it reaches the event horizon, the light emitted becomes infinitely redshifted, and the clock seems to freeze in time. However, from the perspective of the traveler, you would experience no such delay. You would cross the horizon in seconds, unaware of the frozen image you've become to the outside world. The internal geometry of space-time ensures this. Once you cross the horizon, your light cones are tilted so heavily that all paths, regardless of your velocity, point toward the singularity. The interior of a black hole is not a graveyard for data. Instead, modern physics suggests that the universe is strictly information preserving. When matter falls into a black hole, the quantum information it carries is not destroyed. It is scrambled across the event horizon, encoded into the state of the hole. Rather than a void, we view the black hole as a complex storage archive. Information is preserved through quantum states stored on the surface boundary. This realization turns the information paradox on its head. Information is persistent, fundamental, and inextricably woven into the fabric of space-time. How long does a black hole last? While they appear to be eternal traps, quantum physics tells us they actually evaporate over unimaginably long periods. When a high-mass star reaches the end of its life, it collapses. If the remaining core mass is sufficient, it leaves behind a black hole. A solar mass black hole is massive, but it is not infinite. Its mass is tied to the gravitational system it inhabits. Through Hawking radiation, a solar mass black hole slowly loses mass. To completely evaporate, it would take approximately 10 to the power of 67 years. This duration is so vast that for all practical purposes, black holes are essentially permanent features of our current universe. Studying the event horizon is a unique path to understanding the birth of our universe. Consider this. A black hole is essentially the Big Bang process in reverse. Where the Big Bang was an explosive expansion of space, a black hole is a catastrophic collapse. By observing these gravitational giants, we test the extreme physics that govern the origin of all things. They are our ultimate laboratory for quantum gravity. The event horizon serves as our primary frontier in physics, acting as a natural laboratory where the laws of nature are stretched to their limits. Here, general relativity, which governs gravity and the structure of space-time, encounters quantum mechanics, the language of the subatomic world. At this boundary, these two pillars of physics, once thought to be incompatible, must finally converge. Solving the mysteries of the event horizon is essential for our quest to reconcile these theories into a single, unified theory of everything. Historically, we viewed black holes as mysterious, empty voids where everything simply ceased to exist. Today, we understand them differently. Black holes are the most complex information storage devices in the universe. Defined by the intersection of space-time geometry and quantum entanglement, they preserve the history of everything they consume. We have moved from seeing black holes as mysterious voids to viewing them as the most complex information storage devices in the universe, defined by geometry and quantum entanglement.